So those who are present here, please type something in chat box. Only you will be getting your attendance. You can type your USN number or your name. I want you to type something in chat box. Okay, yeah, I've got. Yes. Okay, good. Yeah, yeah. Yeah, you will be fast in this, I guess, right? Okay, so let me see if I ask questions, will you be so fast in answering as well? Okay, we'll check. Fine, fine, fine. Yeah. Okay, stop. Not anyone after this. Okay. Fine. So after McQueen, oh, Freed, after giving attendance, he left, is it? So, okay. So, no, okay, Afrid is here. Fine. We'll start. So, let me put in full screen mode. So, today we will be discussing the topic called AC voltage controller. Again, let me remind you, since I'm in full screen mode and I'm in 2 tabs, I'll not be able to check your chat box. Okay. If you have to say something, if you want to communicate to me, if I'm not reaching you, you have to unmute yourself and speak up. Okay. Fine. So welcome to lecture 25. So in this session, we will be discussing AC voltage controller. All right. See, in power circuits, if thyristor, which we call it as a power device, if thyristor switch is connected between AC supply and load, okay, the power flow can be controlled by varying the RMS value of AC voltage applied to the load. I'll repeat, if you are connecting a power device, that is your thyristor, between supply and load, you can control the power flow, okay, by controlling or varying the RMS value of the AC voltage. So how can we do this? That is nothing but the discussion what we are having in this session. So this power circuit, what I just mentioned, is called AC voltage controller. It is also called AC voltage regulator. Okay. So by the end of this class, today's class, you will be able to describe integral cycle control of AC voltage controller. All right. So what happens here is when we say AC voltage controller, it actually changes the voltage level of the AC signal at the load. Okay. This controller, it changes the voltage level. All right. But there will not be any change in the frequency. I'll repeat, the average voltage, what you're getting at the load, can be controlled by this AC voltage controller. However, there will not be any change in the frequency. Remember, the voltage what is coming to load is AC voltage, all right? So make that point. So there again, the average voltage what is coming to the load, that is AC signal what is coming to the load, can be controlled, okay? So there will be changes in the AC voltage, but there will not be any change in the frequency. So the main application lies here as it is listed here. It is used in the applications where you have industrial heating, speed control of AC drives, or lighting control. Okay, wherever you want to control the speed of a motor or say heating furnace, in such applications, this can be used. Okay, so this power flow, what we are talking about. So this can be controlled, or this there are 2 types of control strategy here. First is the integral cycle control, which is also popularly called as on-off control. And the second is phase control. Okay. So today's class we will be discussing only integral cycle control. Okay. So in on-off control, the thyristor switches connect the load to the AC source for few cycles of the input voltage and then disconnect it for another few cycles. All right. Whereas in phase control, you know how it is done. Phase control, the way, I mean, the time at which you turn on fire the thyristor, you can control the AC voltage because that portion of the input can be available at the output, right? So we will discuss about that later. So as I mentioned, in this method, that is integral cycle control, the load will be connected to supply for only n cycles, okay? And it will be disconnected from supply for, say, m cycles. So what is the use of this? What happens? Imagine if there are applications where the process time constant is quite high, okay? As listed here, for example, heating furnace. Or also you can take the example of speed control of motors, high-speed motors. Okay, so just visualize that. Say you are connecting supply for few cycles and turning it off for a few cycles. So if the time constant of the process is large, then that doesn't make any difference, right? Even the disconnection of the supply for few cycles will not make any significant changes in the process. I hope you are able to get it. All right. So let's see how it happens. So here the waveform representation of what I just narrated is shown here. So you have here this VS, which is your input. So 12 cycles of VS is shown here. Okay. And say for 5 cycles, you're keeping the how to say, the supply is connected to the load for only 5 cycles. N is equal to 5 here. Okay, and supply is disconnected from the load for, say, M is equal to 2 cycles. Okay, so with such kind of process, if the time constant of the process is large, then even if you turn off the supply for few cycles, it will not make any difference in the overall process as such. But of course, in the output voltage, what you get will be different, right? So see here, say if you take for, say, 7 cycles here, the supply is connected to the load for only 5 cycles, and for rest of the 2 cycles it is off, right? So the average output voltage for 7 cycles will be different, right? So the input is this, but if you are calculating the average output voltage will be different. So obviously average output voltage will be different, but as you can also observe here, there will not be any change in the frequencies. Okay, so this type of power circuits are called AC voltage controller, right? So here we have to discuss something about duty cycle. I hope you know what is duty cycle. Duty cycle is nothing but N by N plus M. N is the number of cycles where the circuit is on, where the circuit is on, right? And N plus M is the total time period or total cycles, you can say, right? So here duty cycle K, it is given by N. N is nothing but where the supply is connected to the load, and for total duration, that is the total duration what you are considering for which there is supply and there is no supply. That is, the supply is connected to the load and supply is disconnected from the load. So that is N plus M. So duty cycle is given by K is equal to N by N plus M. All right. So I hope you are noting down all these things. Please let me know if I'm not reaching you, because I'm not able to check the chat box. All right. So there are different parameters what we have to understand here. So this is a simple circuit, AC voltage regulator or AC voltage controller, what you can see to obtain the integral cycle control. Okay, so as you can observe here, there are two thyristors connected in anti-parallel, okay, through which load is connected to the supply. Okay, so observe what happens to get this. What can be done? Say in the positive cycle, when the supply is, say this terminal is positive and this terminal is negative, say if you are triggering T1, if you are turning on T1, obviously recall there is gate circuit which is not shown, but whenever you are discussing about thyristor, you should remember there will be gate triggering circuit, right? So in the positive cycle, if you are turning on T1, then T1 will go into conduction mode. So the current path will be like this, right? Via T1 load and back to the supply. Okay. So when the supply is reversed, that is during the negative cycle. So what happens during negative cycle? This terminal will be negative, so which will turn off T1. Okay, which we call it as line commutation, if you remember, or natural commutation, because of the property of the signal. So that will help the power device to turn off automatically, right? Because of the reverse bias condition. So in the reverse cycle, in the next negative cycle, this terminal of the supply will be positive, this will be negative. So the current will be in this direction when you have turned on or fired T2, isn't it? So observe here. So the operation of this AC voltage controller will be in such a way that in the positive cycle of the input, say at every zero crossing, in the positive cycle, T1 will be fired. So this is the output because of T1 fired. All right. In the negative cycle of the input, observe here at the zero crossing, T2 will be fired. Okay. So this is the output what you are getting. I hope you are able to relate, right? So again, in the next positive cycle, at zero crossing, if T1 is fired, so it will conduct. That means whatever the input you are applying, same will be appearing at the load. So this is our output and this is our input, right? So the same signal is coming at the output. Similarly, at the negative cycle. So this continues, right? So the firing of the thyristors will be at zero crossing. So that is the important point to note. Okay, and it will be fired alternatively. In the positive cycle, T1 will be fired. In the negative cycle, T2 will be fired. All right. So that will give us a AC signal at the load. Got it? Yeah. So in such way, what will happen? We can have as many as cycles of output as required. So in this case, say here n is equal to 5. So depending on the average output, what is required at the load, we can decide to what number of cycles I want to keep the circuit complete so that I will be getting AC signal at the load, right? So based on that, we can trigger or turn on the power devices as shown here. All right. So I hope it is understood. So this will give us the variable AC signal at the load. Okay. So AC voltage regulators are used wherein in situation or applications where you want to vary the fixed AC signal to variable AC signal. Okay. Again here recall that there will be difference in the average AC signal, that is output signal, but there will not be any change in the frequencies. Okay. So in such situation, AC voltage controller or the regulator will come into picture. So in this type of circuit, we will be interested in calculating various parameters for integral cycle control of AC voltage regulator. Let me pause here and see if all are there and alert. So you are able to understand? Can you acknowledge? Can anyone acknowledge? Yes. Okay. Okay. Thank you, Sanket. Fine. So the parameters what we are interested with in this particular circuit, power circuit. So we will be discussing the first parameter here is the VRMS. Okay. So VRMS is represented here as V naught R. R stands for VRMS, RMS output voltage, and not obviously it is about output. Okay. So this is the expression for VRMS. All right. You know the RMS value, it is always taken under square root. Yes. So here it is the RMS value for one cycle can be taken for 1 by 2 pi, which means that the output is available for 2 pi radians, right? So 1 by 2 pi limits between 0 to 2 pi again, because you are taking one complete cycle here. Okay. And Vs square d omega t, isn't it? So Vs is your input, which can be taken as Vm sine omega t, where Vm is the magnitude of your input AC signal. All right. So here you can see one more parameter, n by n plus 1, n plus m, which is our duty cycle. So this is a, why are we actually multiplying this duty cycle? Can anyone tell me? Can you think why duty cycle is multiplied with this expression for VRMS? Because see, the output what we are taking, it is for one complete cycle, right? And it is repeating for this particular duty cycle, which is nothing but for what duration you have output, that is for a number of n cycles where you have output, and the number of cycles where you don't have output, right? So that is the period for this particular expression. Okay, that's why we are multiplying this expression with the duty cycle. All right. So please note down. So if you go through, I mean, complete the expression there, apply integral limits, apply all the expression there. Note down. You will. So here, what this is the same expression what we had in the previous slide. The duty cycle into 1 by 2 pi, 0 to 2 pi. These are the limits for which we are taking for one complete cycle. Vs, small vs is our input. Say it is a sinusoidal AC input. Okay, square d omega t under square root, right? So substituting Vs here, Vm sine omega t whole square. Again, under square root. The whole term is under square root because we are calculating V naught RMS. All right. So Vm constant square, we will take it outside here with from the integration. So 1 by 2 pi, 0 to 2 pi, sine square, sine omega t square, d omega t. Please note down all these things, because I can see the derivations from your answer booklet. It is very disheartening to see your answers. Many of you are not attentive during class. Yeah. So sine square omega t, that is this expression. applying trigonometric equation there, it becomes 1 minus cos omega t by 2. Okay, substituting. So the whole term, if you apply integral, you end up with 1 by 2 there. So n by n plus m, substituting k for that, m square 1 by 2 under 1 by 2, that is under square root, right? So finally you will have square root of k Vm by root 2. Okay, Vm by root 2 is what? It is nothing but the RMS value of input, right? Yeah. So substituting Vs there. Vs here, not here, it is capital Vs, which is the indication that it is RMS value of input. All right. So V naught RMS, it is given by root k into Vs. And please observe here, this Vs is not equal to this Vs. This small Vs is nothing but instantaneous value of input voltage, this Vs. And this capital Vs is the RMS value of the input, okay, which is given by Vm by root 2. I will give some time, please note down. So all these are different expressions related to AC voltage controller, that is integral cycle control, that is on-off method, for on-off method. Can I proceed? Should I wait or I'll proceed? Should I wait or I'll proceed? Okay. So if you're noted, wait, okay, fine. So at least if you respond, I'll come to know what should I do. I hope it is visible. I am out of slideshow mode. So please note down, at the end of the session, you will have to give me answer for a problem, okay? And I'll be randomly calling, so which will be again proof for your attendance. So if you give me answer, that will be a mark or point to your attendance. Fine. Can I proceed? So see, in exam, you can expect some question, something like explain the on-off method of AC voltage controller with relevant expressions, derivations of expressions, and relevant waveform, something like that. Okay, so that is what is covered in this session. All right, next, RMS output voltage. As we have just now derived, it is given by root of k into Vs. Okay, RMS load current, obviously I naught R, it can be represented as I naught R. Okay, so which is given by V naught R by R, right? So just dividing it by R. So this is the expression, please note down. So once you have the expression, when I give a problem, you should be able to substitute values and give me the answer immediately. So that is what I'm expecting here. So output power, P naught, you can take it as P naught, which can be written as V naught R square by R. So it comes to kVs square by R. Or otherwise you can take it as I naught R square into R, right? So both the ways you can write it, output power. So you have to note here, the RMS, as we can recall from the circuit, the RMS input current will be exactly equal to the RMS load current, right? So RMS input current, which you can represent as IS, will be equal to I naught R. Okay, so just make a note of it. Okay, shall I proceed? Can I proceed? Okay, okay, yeah. So remaining expressions, again, these are the expressions which we have already given there in the previous slide. RMS output voltage, RMS load current, output power, RMS input current, and RMS load current. So input volt amperes, it is given by Vs into Is. Okay, since Is is nothing but RMS input current, which is also equal to RMS load current I naught R, we can also write it as input volt amperes can be written as Vs into I naught R. Okay, which is the RMS output current. Okay, so you're just substituting that Vs into V naught R by R. So this is your input volt ampere. So input volt ampere into input power factor will give us output power, right? So from this, the input power factor
Dulu.
Okay, I'm sorry. My laptop hanged, so I had to restart. Sorry for that. Let me open the file. Uh, Oh, there is some problem. My PPT is not. Mm, okay. Okay, let me share screen. Um, I hope, I think I have completed the discussion here. Uh, so you can see the screen, right? Yes, okay, thank you. Thank you. Yeah, fine. So let me check where was I? Uh, yeah, we were in slide number 12. Okay, yeah. Yes, the final average thyristor current, that is when the thyristor is in conduction mode, all right, the current flowing through the thyristor, it can be represented as IT average. Okay, so observe here, each thyristor, it will be conducting for half a cycle, right, from 0 to pi. Okay, so observe the limits there. So the average thyristor current, it is given by IT average. So again, you are to maintain the periodicity, you are multiplying by the duty cycle factor here, n by n plus m into 1 by 2 pi. Okay, because the output is available for the 2 pi radians, the one complete cycle. The limits what you are applying is for particular thyristor, that is 0 to pi. All right. So Im sine omega t is your input. All right. So substituting, you will get K Im by pi. Okay. Applying integral and all. You can do that. All right. RMS thyristor current, which is represented as IT RMS. Again, if you recall, it is you are taking the square of this current, right? Im sine omega t under square root, right? So the whole term under square root n by n plus 1 m into 1 by 2 pi, limits again 0 to pi, Im sine omega t square d omega t, right? So if you apply the limits and integrate that, you will get root k Im by 2. So you can just check it. It is similar to the expression what we had in the previous for V naught RMS, right? So yeah. So with that expressions, I want you to solve this problem and give me the answer right now. So I hope you have copied all the expressions there. And this is the question. An AC voltage controller has a resistive load of R equal to 10 ohms, and the RMS input voltage is Vs given by 120 volts, 60 hertz. The thyristor switch is on for n is equal to 25 cycles, and it is off for m equals 75 cycles. All right. So determine RMS output voltage, that is V naught R. Input power factor is asked, which is given by PF, and also give me average and RMS current of thyristors. So all the expressions, I believe that you have copied. Now we have to just substitute the values given here. Please do it. I will call randomly few of you to give me the answer. So how do you start? What are the things given? R is given 10 ohms. Vs is given 120 volts. So what do you calculate there? What do you need there in your expressions? In your expressions, you need Vm, right? So how do you calculate Vm? How do you calculate Vm from Vs? Hmm? Can anyone tell me? RMS output voltage, V naught RMS is asked. So to get that, the expression what you have for output voltage, that is RMS output voltage V naught R, it is Vs into root K, right? Okay. So what do you substitute there? Vs is what? Vs is, what is Vs? It's given direct value. Yes, 120, correct. Yeah, calculate K. Correct. Yeah, Vs is 120. Calculate K. What is K? Okay, I've got the final answer already. Good. Thank you, Astrid. Yeah. Substituting K, N by N plus M, that is 25 by 100, which you get 0.25. Okay, so Vs into root K, you will have 120 into root of 1.25. Sorry, 0.25, sorry. So it comes to 60 volts, right? All right. What is the second part? What is asked there? Second question, input power factor. So how to calculate input power factor? Can anyone tell me? How do you calculate input power factor from the, yeah. Okay, Abhishek, thank you. You got the answer? Yeah. Yes, correct. Abhishek got the answer. Can you tell me how to calculate, Abhishek? How did you get answer 0.5?
Ma'am, root of K, ma'am.
Root of K. Okay, you can directly substitute there, right? Also, you can also calculate the output power and the input volt amperes. For example, if it is asked, if they split the question and ask you independently, right? Correct. So you can calculate input volt amperes and output power. Yes, that is also fine. Yeah, the last part, the peak thyristor, sorry, what is that? Last part is RMS and average current of thyristors. Who will give me the answer? Let me call someone. Karishma, you're there? Karishma T. Karishma T. It looks like you are here, but you are not here. Are you not there, Karishma? I don't know what you guys. Ria Kutina, are you there? Yeah. Can you try to calculate RMS and average currents? Yeah, try. What's the expression? The average current of thyristor, it is given by K into Im by pi, right? So you need Im there. What is Im? How do you calculate Im? How do you calculate Im? Vm by R, correct. Yeah. So what is Vm? Vm by R is correct. So what is Vm? Vm is 60, huh? No? No? What is Vm? Yeah, 169.7, correct, Valona. Yeah. So it is nothing but Vs into root 2, right? 120 into root 2 is your Vm. 120 into root 2 is your Vm. So which comes to 169.7 volts, right? So from that, Im will be Vm by R, which is 169.7 by 10, which will be equal to 16.97 amperes. Yes, correct, correct. Yeah. Please note the units as well there. You have to mention the units every time whenever you are giving any value of particular parameter. All right. Okay. That is about average current. What about RMS current? Who will give me a, let me see whether you're there or not. Someone. Anil Nair. What is RMS current of thyristor? Anil Nair. I know you're not there. Mohammad Afreed.
No, ma'am.
Okay, Anil Nair, you're there. You ran and came back, hearing your
No, ma'am.
voice. Okay. Can you tell me what is the RMS current of thyristor?
4.24 ampere.
Okay, very good. Thank you. Yes, yes, fine. Yeah. Yeah. Thank you. Yes. So let's go through. I hope that is about AC voltage controller, that is with on-off method, all right, which is also called as integral cycle control. Just go through if you have any clarification at any point. If you want me to repeat any point, we can have. We have still 10 minutes left. Okay, let me ask someone, what have you understood about? Okay, Divij Kumar. Divij Kumar.
Yes, ma'am.
Yeah. Can you tell me what is AC voltage controller?
An AC voltage controller is a one.
Yes. Is the one. The name itself suggests. Just you have to just
Yeah, it
think.
controls the power by varying AC voltage, keeping the
Control.
frequency.
No. Just think about it. Controls the power by varying the AC voltage. Okay.
Control output power, I guess.
Okay.
Output voltage.
Yes,
By
your answer.
varying the RMS voltage, keeping the
Okay.
frequency constant.
Yeah. So first, see, in simple words to say, it's a power circuit which will control the AC power that is fed to the load. Okay. Simple words.
Okay.
AC voltage controller is a power circuit which controls the AC power to the load, right? So that means the load will be getting AC signal. Okay. Using this power circuit, you can control the AC signal that is fed to the load. All right. So how do we do that? That is the two methods what we have just discussed. One is the integral cycle control method and other is the phase control method. Okay. Okay. Thank you, Divesh. Okay. Let me ask someone else. Sanjan. Sanjan, can you come in? Sanjan, yes. Can you? Why don't you unmute yourself and speak? Why don't you unmute yourself and speak, Sanjan? I'm having issues with mic. Okay, yeah. That's a very common and default answer these days. I have network issues. I have problem with mic. Sachin Shetty. Sachin Shetty. Who is this Sachin Shetty? You're not there at all. Sachin Shetty, are you there? I hope you should be knowing that these meetings are recorded and I will come to know who are there and who are not. Yes. Even you have mic problem? You cannot unmute and speak? Princita D'Souza. Yeah, can you tell me what is this on-off control? How it is done? What is on-off control?
Connect to the load.
Mm-hmm.
An AC source for a cycle input voltage in disconnect with another M cycle. Connect.
Okay. So, all right. So the question what I asked was, what is on-off control? How it is done? Okay. So obviously what we are discussing is AC voltage regulator or controller. As I said, you're controlling the AC signal to the load, right? So say out of 10 input cycles, if you are keeping the power device on for few cycles, so which is nothing but you are connecting supply to the load, right? And keeping the supply off for few cycles. Okay. So what happens if you measure the average AC signal at the load? Obviously, it will be different, right? It will be different from the input. So that's what I had shown here in the figure as well here. So look at this. If this is your input, let me go. Yeah, if this is your input wherein you have 12 cycles. Okay, let us take only 7 cycles here up till here. For 7 cycles of input, okay, if you keep the circuit on, in other words to say, if you connect supply to the load, okay, you are getting AC signal at the load, say for only 5 cycles, and you are disconnecting the supply to the load for rest of the 2 cycles, that is M is equal to 2. When you calculate the average AC signal at the load here, it will be obviously different from this, right? Yeah, right? So you're controlling the AC signal. You're controlling the AC power that is fed to the load, keeping it on for a few cycles and keeping it off for a few cycles. You're getting a varied AC signal at the load. Okay, that is the simple way of representing things. I hope it is understood. Okay, so this is the circuit used for that. How do you do that? This is a circuit for that. Okay, like how many cycles you want to keep the supply connected to the load, you are triggering or turning on the thyristors here. All right. So see, all these circuits what we have discussed till now, it can be DC to DC converter, AC to DC converter, or AC to AC converter, which we are discussing now. All these converters are nothing but what we call it, give them different name because of the configuration, how we are using your power devices. I hope you are able to relate that. The way you design and use the power device, that will give a different working and applications, right? Where you can use it for different applications. So, okay. Now, I want every one of you to type something in chat box. So which will give me, just in 1 minute, which will give me how many are there now. 49 are there in B section and 59 are there in A section. 59, all are there in A section. Okay, except one, I don't know. Yeah. Yes, thank you. I hope it is understood. If you have any problem, please get back to me. Don't sit with the doubts. Or if you want me to share some material, please ask for it. Yes. Okay, guys, that's it for the day. Let me take this. This is B section. B section. Shit. Yeah, thank you. You can leave. Yeah, thank you. And this is A section. Okay. Yeah, you can leave. Thank you. Yes.
I'm Sean. I have
Sean.
a doubt.
Yeah, Sean, tell me.
Yeah, in the offside, are you switching off the VS supply or are you increasing the gate voltage across the transistor?
Come again?
Like, are we switching off the supply now at the off terminal?
Okay.
Off at off m equal to 2.
Here. Okay, yeah. Keeping off the supply means what? You are not triggering these thyristors. That means
Or
yeah,
increasing the threshold voltage of the thyristors.
increasing the
Threshold voltage.
no. See, if you don't turn on these thyristors, the circuit is not complete, right?
Like question mark. So
yeah.
now imagine the thyristors aren't there. So only if we are giving the supply over there, if you see at on n equal to 5, after that off, what if is off the supply over there and later if on the supply, it will be a same waveform.
No. I'm not able to get your answer. I mean question. See, observe the waveform here. If this cycle, this positive cycle, if you can see this, what does it represent? You have turned on thyristor T1, and this is the output what you are getting, which is nothing but the supply following at the output, right?
Correct.
Yeah. Okay. And in the
What if the thyristors weren't there?
Weren't there? Okay, that is different application, right? Now we are talking. Okay.
Yeah, the waveform is the same, no? Even if you off when you are equal to 2, the supply will be off.
Yeah. Okay, so I think your question is, what is the role of thyristor? Is that so?
No, if thyristor weren't there, you get the same waveform.
You will get the same waveform, but yeah, so you have to understand what is the role of thyristor, right? Here again, you can control, you have the decision to when to fire these thyristors, right? Which will be controlling the output voltage. So that is what we are looking at, like in power circuits. So here thyristors, we know that according to the specifications, it can withstand high voltage, right? So where applications with high voltage, okay, and like what is the average output voltage that we want at the load, there such power circuits will come into picture. I guess I'm able to answer your question. Huh? Yeah. Okay. Thank you. Yes, fine.